Hi everyone, I'm Xinlei Chen from Carnegie Mellon University. Today I'm very happy to talk about our work, DrunkWalk. It is a collaborative and adaptive planning for indoor swarm navigations. So as we all know, in urban search and rescue, it is very essential to get some information at some key locations. However, in such scenarios, the pre-deployed sensing system may be damaged or even destroyed, and also it is dangerous for human beings to access. For example, we have a house and catch fire near kitchens, and also we have some survivors hiding in their bedrooms and waiting for people to uh, help them. And if we can send these small drones to these key locations, then we can figure out first the location of these survivors and also some suitable route to enter and escape. And also we can figure out some dangerous areas that like firefighters can avoid because they are very dangerous for anybody to get to these locations. And compared to traditional robots, MAV has some advantages. First, they are very low cost, which allows large-scale deployment. And also, through redundancy, we can achieve high reliabilities. And also, these small drones are very light. So this lightweight will prevent serious injury to human beings. So this brings us to the goal of this paper, navigating flying drones to a set of goal areas automatically. Before we can achieve this goal, there are two constraints we have to face. The first one is it is unlikely to have external sensing infrastructure because first, there might be no pre-deployed infrastructure to be used. And second, even if there's some infrastructure that we can use, they may be damaged in a disaster like fire. And the second constraint is the limited onboard resource like sensing, computing, and communications, because these drones are very low cost, so we cannot afford, and also very light, so we cannot afford very complicated like CPU or like sensors or like communication parts. So after talking about the motivation, let's see what's the existing solutions. So the first group of existing work is external sensing infrastructure-based method. So they use some pre-deployed external sensing infrastructure like these cameras to do both localizations and navigations and can achieve very high navigation accuracy. But the problem is they rely on the infrastructure pre-deployed, which is impossible in emergency scenarios. And the second group is pre-survey-based method. And before this method, before operation, they first survey the environment. And during the operation, based on the signature matching, and the system can do localization and navigation. But this method, the problem of this method are like they also rely on the infrastructure, and also they require a pre-surveyed period, which is also impossible in emergency scenarios. And the third one, they didn't. But this figure also gives us some interesting observation. If we can combine these very bad location estimation together, probably we can get better results. That's also the intuition of our work. So let's look at our solutions. So how we plan to conquer these two constraints and challenges. So for the first one, we plan to disperse some drones to self-establish temporary sensing infrastructures. And for the second one, we try to combine this noisy directing location estimation from multiple drones at the same place they pass by. And in order to achieve this, we designed the workflow like as setup, location estimation, and path planning. These two work in conjunction. So setup period is like the initialization period of the system. And the location estimation, so before path planning, we need to do location estimation first. Because if we don't know where we are, we cannot know where we should go. And then we go to the path planning. So during setup period, we first disperse several drones and land them as beacons to broadcast radios. These green squares are the landed beacons. And they spread away from each other until they encounter some obstacles or lose range render with each others. It is noticed that we do not know the location of these landed drones, so they might be landing at any locations as long as they meet these two requirements. And that's why we cannot use the traditional trilateration method like GPS to do the localization in our problems. And after the setup period, we enter the location estimation period. So first, we introduce some flying drones into the operating environment. And these drones fly around, and we call this a trace. And in order to track the trace, like the location and the orientation of the MAVs, we use particle filters to track that. Because the noise of indoor localization is non-linear and non-Gaussian, so that's why we use particle filters. Here we want to estimate the states xi, that is the location and orientation of the MAVs. And we know we can get the transition between xi and xi minus 1 through gyro and optical flow. Gyro gives us the rotations, and optical flow gives us the velocities. And also, we can get the observation yi through magnetometers. Magnetometers basically gives us the orientations. And then finally, we can get the distribution for location estimation. So here it seems very perfect that only particle filters can solve these problems. But we have to notice the sensors are very noisy, like magnetometers. Sometimes it gives us like more than 100-degree errors. So both like prediction step and also the correction step, we have very big errors. So that will probably lead to very bad location estimation. That's why even with particle filters, we still need to combine these location estimations together to improve the performance. And in order to combine this location estimation, first we need to discover the intersection in the trees, because only after we find these intersections, then we can combine the estimation together. So John 1 discovered the signature from all these green beacons in their traces. And a signature consists of the signal strength from all these beacons. And after another drone hit the same point, the system based on the similar signature pattern and decide that is intersections. And here we call it a snapshot point. And after we got these snapshot points, we can combine location estimation together. So when the first drone passed by the snapshot point, we just copy the location estimation distribution from this drone because we only have one. There's no others to be combined. And after the second one passing by the same snapshot point, then we combine them together and to improve the estimations. And then we have the third one, the fourth one, to further improve the location estimations. And now let me give you some more details about how we combine these distributions. First, we have particle filters for MAV locations. And also we have particle filters for snapshot location, that is the combined particle filters. So at time t, we have particles and weights from MAV location particle filters, and we can calculate the weighted average location x bar. And using this x bar and the particles and weights at time t-1 from particle filters for snapshot point, we can do correction for location estimation, and finally figure out the new particles and weight for particle filters for snapshot point. The basic idea here is based on the Euclidean distance between X bar and particles from these particle filters. We recalculate the weight and particles. So usually the short distance will lead to the heavier weight here. And here comes up question. If we don't know where we are, we don't know where to go. That means if here we get very bad location estimations, then we cannot guide the drones to the destination correctly. The performance might be similar to DrunkWalk, to random walk, or even worse than random walk. But in real scenario, we cannot really know how accurate we are because we cannot get the ground truth during the operation process. But what we can get is we can know how much confidence do we have in location estimations. That is location estimation certainty. This brings us to our adaptive planning strategies. So first, we use the information entropy of the estimation distribution to measure certainty of location estimation. If the certainty is high, that means we are pretty sure where we are. Then the system will direct the drones towards the goal area. And if the certainty is low, that means we don't know or we are not sure about where we are. Then what we can do is randomly pick up the movement and the rotation according to the uniform distribution and try to increase the snapshot point. Because if we increase the snapshot point, we can further improve the location estimations. Then we can move forward to this status and navigate the drones to the goal areas. And I've talked about the solutions. Let me introduce how we evaluate our systems. So we both evaluate the performance and the reliability of our systems. Performance here, I mean localization accuracy and navigation success rate at a given constraint. And we do both real experiments and physical feature-based simulations. We use dead reckoning with map bias as the baseline. So the baseline use dead reckoning to do localization and use the map information to do navigations. And this figure shows the operating environment for both our experiments and simulations. We set up some different goal areas to represent the different navigation lengths and difficulties. So for real experiment, we do 5 experiments to get the average and the standard deviations. The x-axis is the percentage of navigation time, and the y-axis is the location estimation errors. And the red line is our result, and the blue line is the baseline. So at the first 20%, our system performs similarly as the baseline. This is because at this first beginning, our system does not have enough time to get enough snapshot points to correct the location estimation errors. But after this initial period, we can see an increasing gap between our result and the baseline. And during this period, the system corrects enough snapshot points to help correct the location estimation errors. And also we can see that for average location estimation error, our system is control the error below 2.5 meters, and the baseline always keeps on accumulate. And also from the standard deviation for both our method and the baseline. So we can see we really improve the reliability of the system. And after the real experiment, we collect the profile of the signature and the noise of sensors to implement physical feature-based simulations to evaluate our system at a large scale. So here we do all the experiments 25 times and get the average values. And the maximum running period is 600 seconds because this is similar to the real battery life. And we use the success rate to measure the navigation performance. Successful navigation means that we can navigate a drone to the assigned areas within the given time. So this figure shows success rates and different destination accuracy constraints. So the x-axis is the destination accuracy constraints, which is the size of the destination areas. So usually the small number means the difficult navigation. And the y-axis is the success rate. And here we set up the time limitation as 90 seconds. That means only drones that can be navigated to the goal area within 90 seconds can be regarded as a successful navigation. And when the constraint is very strict, like 0.5 meters, the baseline can only achieve very bad, like 5% success rates, while our system can achieve like acceptable around 40% success rate. After we lose the constraint to from 1 meter to 2 meters, we can see like stable advantage around 30% to 40% of our system over the baselines. And also we can see that DrunkWalk can achieve up to 3 times improvement in success rates. Another important, interesting problem we care about is how different setup of the system affect our system performance and the reliabilities. Here we choose the different number of landed drones. So the x-axis is the number of stationary MAV nodes, and the y-axis is the location estimation errors. It is noticed that the baseline does not use the landed drones, and this variation is due to the noise from different runs, and they are basically similar. And from here we can see like obvious decreasing trend when the number of stationary nodes increase. This is because when we increase the number of these stationary nodes, actually they help improve the signature matching performance. And by improve the signature matching, and it helps to do location estimation correction better. And also we can see that DrunkWalk achieves 1.5 times to 6 times reduction for average, and 1.5 times to 4 times reduction for standard deviation. This shows our system's good ability and reliability for location estimations. And now we can come to the conclusions. So in this paper, we propose a collaborative and adaptive planning for indoor MAV navigations. We rely on collaborations to overcome limitation of individual nodes, and we adaptively plan routes of drones according to the quality, that is certainty of the location estimations. And we, based on the real experiment and large-scale physical feature-based simulations, we prove that our system can achieve around 6 times reduction in location estimation errors and around 3 times improvement in navigation success rates. Yes, thank you for your attention. I'm happy to answer any questions related to this paper. Thank you.